Welcome again to another exciting edition of AP Statistics Special Problems. So here is the special problem for Chapter 4. You can see the topic. We're looking at annual world crude oil production. And notice it starts in 1880, and we're talking about millions of barrels. On the last special problem, things were in thousands, right? And some people didn't pay attention to that. Okay, this says we're in millions of barrels, so you'll want to pay attention to the labeling. Okay, letter A, we're going to make a scatter plot, but make sure you use years after 1800. So 1880 should be entered as just 80, 1890 is 90. So they're transforming the data, giving us some smaller values, so hopefully our calculator can handle them. Okay, so that's what the data should look like. Let's make our scatter plot. And this is what we get. Okay. So comment on what we see. All right. Let's just kind of sketch that real quick on our paper. Okay. I'm noticing what appears to be a concave up, curved trend, but then right here, the pattern breaks, right? Something happens right in here, and I see a change in the pattern. So again, this is common in the real world. I would probably think of interpreting this as a piecewise function, where this piece right here has a real nice concave up trend, and then look at this piece over here separately. Okay, so let's go ahead and sketch that. And again, I'm just going to kind of freehand things. So, and then we have like a little break in the pattern. Something like that. And this is years after 1800. And this is world crude oil production. Okay, so something like that. And again, commenting. This is letter A. I see a concave up, curved relationship until, here's where trace will come in handy. Let's see where this happens. So it looks like between 1970 and 1980, the trend breaks until the 1970s. Trend changes. Okay, so there's letter A. All right, letter B. It appears no single model will describe the relationship. As we just noticed, right, the graph clearly has a change there in the 70s. Okay, so let's make a scatter plot up to 1970. And again, use years after 1800. And then let's try to linearize that data and come up with a model and, of course, justify our model. Okay, so the way to do that is basically just erase the data from this point on. Okay, so the way to erase, you'll notice I just go on what I want to erase, and then I press delete. Okay, please, however, do not delete your list, right? Don't go at the top and highlight list 1 and press delete, or you won't have a list 1 anymore. You can get it back, of course, but it's a pain. All right, so now I have the data. Let's zoom stat. And wow, that looks like a nice, clean curve. Okay, so let's draw that on our paper. very straight, but years after 1800, and again, world crude oil production. All right, I can clearly tell that this is not linear, so I'm not even going to bother with linear because we already noticed this is concave up. It's clearly curved, okay? So we have to use our transformations to linearize the data. I'll go ahead and real quickly see if I can just do an exponential regression and a power regression and see if maybe the correlations are clearly different. I have a feeling they're not going to be that different because this is such a clean curve. I think either method should probably produce pretty good correlations, but let's give it a shot. So let's see. Exponential regression. I won't even bother storing it at this point. Let's just see what we get there. Okay, and sure enough, that's a very strong correlation, 0.997. Okay, so I'm just going to kind of jot that down. Exponential R equals 997. Okay, now I'm going to do power. And 0.9975. I mean, that was 0.997 something, right? And 0.9975. So these things are a dead heat, right? It's really close. So that's kind of what I assumed would happen because that's why it's a practice AP question, right? If it was such a super clear-cut difference, they wouldn't be asking. All right. So now the only way to tell is with a residual plot. So we really need to transform the data and make residual plots. Okay, so let's do that. I know I'm going to do both, so I'm going to go ahead and log my x here, log my y. Okay, and here we go. Linear regression on x is staying x, and log y. Got to store that. Okay, I get the same correlation. That means, yay, I used the right lists. Now that I have it stored, I can go ahead and get my residuals. So my residuals would be the observed log, which is in list 4, minus my predicted log, which plugs in, right, the regular x value, because it's exponential. Okay, so now residual plot will be list 1 and list 5. Oops, up here. List 1, list 5. And there's our residual plot for exponential. Doesn't really look all that random scatter to me, right? So let's just kind of sketch this here real quick. Point down there, above. Okay, so that's the exponential. Let's hope power has a better looking residual plot. Okay, so for power, again, we got to do linear regression. This time it's log of both variables. I'll store that in y sub 2. And again, that's the correct correlation, so I know I used the right lists. And now I can calculate my residuals. Okay, so for power residuals, it's the log of the y's minus our predicted. Again, I've got my equation stored in y sub 2. And here, this equation is based on log x values, so I got to plug list 3 values in there. Okay, now for the residual plot, again on the linearized data. So that would be list 3 for X and list 6 for residual. And here's my residual plot for power. So I got a couple here above, and then a couple below again, and something like that. Neither one looks great, but if I have to pick, I think I'm going to pick the power. If you made a case that it's a tie, I would probably let that slide as a tie because they're pretty similar. Okay, neither's showing a real nice random scatter throughout, right? Both of them are, points on one side, points on the other, as opposed to just bouncing back and forth throughout. But I think I'll go with power. So I'm going to say the power model has an extremely strong correlation. And a slightly more random out of paper. Scatter. In the residual plot. Okay. Both methods, however, really strong correlations. I'd like to see more random scatter in the residual plot, but they're probably both pretty good at predicting. Okay, let's look at the next question. Use your model to predict crude oil production in 1974. Okay. So let's write our model down. And again, I'm going to use the power feature, so make sure you put list 1, list 2. That's when the data is curved. Okay. And again, if you were to use the wrong list, you'd hopefully notice, hey, that's not the correlation I should be getting. That is the correlation I should be getting, so this is the correct equation. Okay, so y hat equals, that's scientific notation, right? So 8.6 times 10 to the negative 15. Wow, that's quite a small coefficient. Multiplied by x raised to 8.14. Okay, so there's our model. Now let's do a prediction for, what year was it? 1974. Okay. Ooh, careful, don't put in 1974, right? It's years after 1800, so that's 174 years after 1800. And again, that's the work, but I'm actually going to be using the equation that I just stored. So that way I don't have any round off error. All right, so there's my prediction. I guess round that off to this, and this is again million barrels. Okay, so how do we feel about this, right? Well, look at the data. 1970 is more. Right? That I don't feel so good, right? I was seeing a continual growth, so I would expect 1974 to be more than the 16,690. So maybe this isn't the best. I think I'll, just for fun, say let's try the exponential to see what we get there. So. Okay, so calculate the exponential again. Oops. I'll just I'll put in, well, this too, whatever. Okay. Oh, yeah, 9974, and the other one was 9975. So, yeah, these are really close. Okay, let's get our equation written down here. Well, I can say this, at least the exponential has a easier to work with coefficient there, right? All right, let's make our prediction. Okay, and we get at least a number that's greater than the 1970. So that's a good sign. And again, million barrels. Okay, so that's good. At least it's more than 1970, but it's also more than 1980. So I feel like this method has overshot and the power came up short. So I don't like either of these predictions, which is strange at first glance because you're like, wait a minute, both had such strong correlations and the curve looks so smooth and nice. But here's the reason, right? It's extrapolation. My last data point was 1970. Remember, I deleted the data points after 1970. So that's why I'm getting a value from one model that's clearly too low and from the other model that's clearly too high, right? That's one of the dangers of extrapolating. So I'm going to say neither model gives a good prediction due to extrapolation. Okay, the power model is too low, and the exponential is too high. Okay, and again, extrapolation kind of shot us in the foot. Not to mention, by the way, right, this is right when everything was changing, right? Things felt good up to 1970. So if they asked me to predict 1964, I bet I would have got a pretty nice number. But they asked me to predict 1974, and that's going into the future and into a region of the graph that it changed, right? Okay. Letter D, make a scatter plot of the data from 1980 to 2010. Again, use years after 1800. All right, so I got to start all over. I deleted that. Okay, from 1980, so that's 180 years after. And over here. All right. And there we go. There's, oh, we got some lines going. Forgot to delete those. By the way, you can look up here and see the calculator still working on graphing one of the equations. So you got to let it finish before we can clear those things out. But anyway, talking about the scatter plot, looks to be, again, concave up. But there's only 4 data points, so it's always hard to really read the graph of only 4 data points and be real confident in what you have. Okay, so linear power exponential, let's give it a shot. So just for fun, I'll try linear because it's only 4 points, even though it looks to be clearly curved. May as well store it. Okay, so there's linear. Okay, and my correlation's actually fairly strong, roughly 0.96. So even though I'm drawing a line through a curve, since it's a short distance, the line isn't that bad. Okay, but I don't like it. Let's move on. Let's try exponential. There's exponential. I was actually thinking I would get a stronger correlation than that because I did see a concave up relationship, but this correlation's basically in line with linear, oddly enough. So that's kind of surprising. There's a different color here. Okay, so that's kind of surprising. Let me look at the graph of that. That's linear. And there's our exponential. Yeah, not that far apart, really. Hard to even see the difference. Really, I think if we could add a C, right, on the end, then exponential would fit it quite nicely. But without a C, having to start at the origin, it's not so great. Well, not really the origin, but close, right? When I'm talking about millions of barrels, yeah. Okay, let's try power. Maybe it'll be better. And there's power. Oh, they're all really close. Okay, 16.6 next to 1.38 R. So yeah, no clear-cut winner. How about we'll look at that power graph? Just to make it easier to see, I'm gonna get rid of those. Yeah, it's looking a lot like the linear and a lot like the exponential. And again, this is something that happens when I have such a small number of data points, right? I only have 4 pieces of data. And the fact that I can't add a constant to either of these, makes my left end of my graph quite low. So it doesn't fit all that well. Okay, so none of those are a great fit, but I got to pick. So let's look at residual plots. Maybe one of them will have a better residual plot than the others, okay? So here we go. For linear, I'm ready to roll with my residuals. Observed y minus predicted y. And let's do our graph. List 1, list 3. And there we go. You know, bit of a curve, as we already knew when we looked at the, let me turn this one off so I don't have to sit through it every time. We already kind of saw that curve earlier, so just kind of sketch it over here, the high point, and then something like that. All right, let's try exponential. Hopefully it's better. I'm going to have to linearize my data, so I may as well make list 3 log of x because I'm going there on the next part. Y. List 4 is my log of y. I'll just overwrite the first one again. Just keep using that slot. Okay, that's the right correlation, so I'm good. And residuals. Observed log of y minus predicted. And list 1, list 5. Yeah, they look pretty similar, as they should, right? Remember, on the actual scatter plot, the two are almost indistinguishable. So, all right, we got that point above, we got the 2 below, and then one more above again. So, pretty indistinguishable between both the correlations and the residual plots. Let's just go ahead and complete this with our power. Okay, that's list 3, list 4, right? Both variables being logged. And sure enough, that's the correct correlation for power. Okay, residuals, the observed log of y minus our predicted, which we plug in the log of x to use. Okay, log of x is list 3, so list 3, list 6. And lo and behold, again, remember that line was pretty indistinguishable from the other two, and the residual plot also indistinguishable. So they all are the same. So even though the data is clearly curved, none of these models can match the curve because there's so few data points and it's so far from the origin, really. We need a plus C on either one of those to make it a better fit. So I'm just going to say it's a tie. So all 3 models are equal, or equally effective, equally good. Okay. They all have strong correlations. Of 0.96 and identical residual plots. Okay, so this is just a flat out tie. Okay, letter E. Use your model from D to predict crude oil for 2016. How do you feel? Support your answer. Okay, let's make our prediction. So I said it's a tie, so I'll predict with all three. So let's start with linear. What was it? 2016. Let's see, 2016 would be 216 years after 1800. I'm not sure what I have stored where, so I'm going to just be safe here and recalculate the exponential regression. List 1, list 4. Oh, exponential. What am I doing? Linear. Sorry. Forget that. Erase. Start over. Okay, so linear. There we go. And now that it's stored, I can go ahead and use it. And there we go. So linear predicts 27,273 million barrels. Okay, let's do the same for exponential. Oops. Okay, and again, I'm not sure where I have that. I'm just going to recalculate it to be safe. Okay, store that. And calculate. And we get 27,408, so a little bit more, but not that different. And not surprising, the models were almost right on top of each other when we graphed them both, right? Okay, let's finish it off and do a power. Yeah, write that down real quick. Okay, and calculate. And hey, look at that. Something right in between the other two, which makes sense. Remember, exponential is always going to be your fastest growth curve. And of course, power will outpace linear. So we get something right in the middle. All right, so since I said it's a tie, I went ahead and did all three methods. And you know what? They're pretty darn close. Oh, actually, what was I saying? Looks like linear was still ahead of power at this point, right? It hasn't quite caught up. So power's the lowest, not in the middle, but it will eventually pass linear. Okay, we made our prediction, and really, my goodness, they're all basically the same prediction, right? They're not that different. So all three models predict a similar oil production for 2016. And we can look at the 2010 data, 26, 7, 24. These all three are 27 whatever. So it's showing growth, which again, we see growth every year. So even though it is extrapolation, it seems reasonable, right? So it seems reasonable, but we must be careful when extrapolating. Yep. Okay. So that was fun. Oh, one thing I forgot to even talk about, should have probably talked about it. If we went back to that original data and we said it changed it changed right here in the 1970s. Hopefully you guys have a little bit of history under your belts. Think for a moment, why did the oil production change in the 1970s? Right, so you didn't live through the 70s, but you hopefully know about the oil embargo and the big crisis of the 70s as far as trying to get gas in the U.S. at least. This is when OPEC started flexing their might, so to say. So you could say. So, yeah, it's not a surprise that we see a big change in the pattern in the 70s. Okay, so hopefully that made sense, and thanks for watching.